Well, hello, ladies and gents. So we begin looking at water potential. So again, water potential basically lets us track the direction of water flow into or out of cells. So when we perform this calculation, we can calculate water potential values inside and outside of cells and track the direction that water will tend to move. So let's read the background statement here. It begins, water potential is a measure of the tendency of water to move from one location to another. Water moves from an area of high water potential to an area of lower water potential. You might wish to highlight that because that's sort of the key idea or the driver. Water flows from high to low potential. I just think of it as sort of like water flowing downhill. Okay, so water flows from areas of higher water potential to lower water potential. Okay, water potential itself, it's affected by two factors. They are the pressure in the system and the amount of solute in the system. The amount of pressure is referred to as pressure potential, and factors that related to solute are collectively referred to as solute potential. So there are a number of factors related to solute potential. So water potential is calculated with this equation that we see here. Water potential equals your pressure potential plus your solute potential. So you have the little psi, and then the subscript P or subscript S to indicate pressure potential and solute potential. Of course, this equation will be provided on the equation sheet, so you don't have to memorize it. You just got to be able to use it. All right, here's another thing that you maybe would highlight. Pure water in an open container has a water potential of 0. If solute is added, solute potential drops, so it actually becomes more negative, and as a result, water potential will drop as well. So again, the thing I would highlight, that water potential in an open container has pure water, so water with no solute. In an open container has a water potential of 0. That will be an important one to remember, because sometimes on story problems, they'll just say something is in an open container or it's in a beaker or something like that. They won't say, hey, pressure potential 0, but you have to remember that's the implication. Okay. So the one thing you need to remember is solute potential and how it is calculated. So if we look at solute potential, there are a few terms that you need to work in here. So solute potential equals minus, and that's a little minus sign here, but it's minus ICRT. Now let's talk about what these different terms mean. I is your ionization constant. It's basically the number of pieces that your solute will dissolve into, if it will dissolve into any pieces. So things like glucose that just forms rings, it'll stay a single particle, so its ionization constant is 1. Something like sodium chloride that will dissolve and form a couple of ions, its ionization constant is 2. So sometimes they'll say, the substance will dissolve into 2 particles. Other times they would want you to know, like if they mention it being a carb, that it would have an ionization constant of 1. Okay, so again, glucose has an ionization constant of 1. Salt, the other common solute that they use, has an ionization constant of 2. C just stands for molar concentration. So again, they'll give you the concentration. So that's pretty straightforward. R is a constant. It's minus 0.0831. And that, again, that's the number you just always plug in. And then the only other trick that they have with this is that the temperature is in Kelvin. So it's 273 plus the temperature in Celsius. A lot of times what you'll see in story problems is they'll give you the temperature in Celsius and you have to convert it to Kelvin. Okay, so the only two real tricks are you need to pay close attention to the ionization constant. How many pieces does it break into, if it breaks into any? And the second thing is to make sure you have temperature in Kelvin. All right, so let's look at this first scenario here. It says you have calculate the solute potential. So you just want the solute potential. 1 molar solution of sodium chloride at 37 degrees Celsius. So solute potential. Let me make this bar a little thicker, if I can figure that out. Nope, don't know how. Sorry, but at least I got a darker color. So solute potential equals a negative ICRT. Now, I, the ionization constant, sodium chloride, so that value is going to be 2. C, the concentration. What did they say? It was 1 molar. R, that's your constant, right? So that's 0.0831. And then the temperature is 37. And again, we have to convert this to Kelvin. So it's 273 plus 37. All right. Well, of course, I don't have a calculator on me. Let me bust out my phone here and see what we can come up with. So 2 times 0.0 is 32, 310. So it looks like minus 51.5, and the unit is bars. Okay, so it's minus 51. Oops, I think it was 51.5. I already deleted it. Minus 51.5 bars. All right, so that's how you would calculate solute potential in this particular scenario. Okay, so now let me try and move the document along here. It says, notice the negative sign in the solute potential equation. If you increase the concentration of solution in the previous question to negative 2 molar, what would happen to the solute potential? So if we go from 1 molar to 2 molar, what did we say it was? Minus 51.5 or something like that, minus 52.5. If it was negative 51.5, then the value would be, what, minus 103 bars. So if the solute concentration goes up, solute potential goes down. Please burn that into your mind because that's an important thing to remember. When solute concentration goes up, solute potential goes down or becomes more negative. And if solute potential becomes more negative, think of the impact on water potential, right? Let's look back at this equation. Water potential is pressure potential plus solute potential. Remember, solute potential is a negative term. So if solute potential becomes more and more negative, what's that going to do to water potential? It's going to make it lower and lower. So if solute concentration goes up, water potential goes down. And if water potential goes down, well, water flows from high to low potential, right? So if you have a hypertonic solution that has a really high solute concentration outside the cell, that high solute concentration makes the water potential much lower. And since water flows from high to low potential, water will flow out of the cell. So that gives us our justification for why water flows in a particular direction. So the thing, again, just remember, when solute concentration goes up, water potential goes down. Let's see, the next statement. Water flowing into a cell would increase the pressure potential in the cell, which makes sense, right? Water flows in, the pressure on the walls will be greater. If it's a sealed container, think of like a cell. If water flows in, pressure will go up, right? And so if pressure potential goes up, eventually pressure potential and solute potential will cancel one another out. Because again, solute potential has a negative value, right? So if you have a solute dissolved in a cell, it has a negative water potential, and water will flow into a cell. But as water flows in, pressure in the cell will increase, and eventually pressure potential gets high enough that if your solute potential is minus 2 and your pressure potential becomes plus 2, then you will have those cancel one another out and your water potential becomes 0. All right, so water flowing into a cell would increase pressure potential, sure. What impact would increasing the pressure potential have on the water potential in your system? Well, if water potential is pressure potential plus solute potential and the pressure goes up, then water potential will go up. When pressure potential equals the solute potential, water potential is 0, sure. Describe the flow of water in such a system. If you have water potential of 0 inside and outside the cell, or the difference in water potential is the same inside and outside the cell, then you have a net flow of 0. Water will flow in and out, just flows in and out at the same rate. Let's see. Why is there pressure potential in a closed container? Well, think about a sealed container. As water flows in, the water will push on the walls of the container, and the walls of the container will push back on the water. So the pressure in the system will increase. So as water flows in and it pushes on the walls of the container, and the container pushes back on that water, the pressure in the system will go up. Let's see. If you were to place a leaf of Alodia, an aquatic plant, in a beaker of distilled water, in what direction would the water flow, into or out of the cell? Well, let's imagine here. Let's say we have a beaker with some water, and it's distilled water, so it's just pure water. And then we put an Alodia plant in there. Plants have solutes in them, right? So we can imagine little dots in here for the solute. Well, when solute concentration goes up, what happens to water potential? That's right, it goes down. So because there are solutes dissolved in the Alodia plant, it will have a negative water potential, and water flows from high to low potential, so water will flow in to the cell. Okay, so again, because there are solutes dissolved in the Alodia plant, its water potential drops below zero, and because it has a lower water potential and water flows from high to low potential, water will flow into the cell. A recommendation I have, like a rule of thumb, is to just remember water follows a solute. Wherever solute concentration is greater, there too shall go water. So water follows a solute by and large, unless you have issues with pressure building. But by and large, because increasing solute concentration decreases water potential, water will tend to flow in that direction. Let's see. Here's a great question. Explain what impacts the water potential inside the Alodia cell. So, I'm sorry, not water potential, solute potential. So if we think about that, what impacts solute potential inside the cell? There's a reference for you. It's right here. Solute potential equals your minus ICRT, right? So if they ask what influences solute potential, you could say the number of particles, the concentration of the solute, and the temperature in Kelvin. There are three things there. So on the AP exam, they could ask you what influences something like solute potential. They're not asking you to necessarily memorize it. They want you to be able to look back at the equation and make sense of what the equation is telling you. That's what that problem is about. Okay? So when they say, okay, what influences solute potential? If you don't know it off the top of your head, use your equation sheet as a resource. Okay? They'll ask you questions like that on the AP exam where it'll be like, what factors could influence something? And if those factors or those variables are in an equation, you can just reference the equation and use it as a resource. So again, what impacts solute potential? The number of particles the solute will dissolve into, the concentration of the solute, and the temperature of the system in Kelvin. Okay. One last thing. Calculate water potential for the following scenario. 1 molar solution of glucose at 35 degrees Celsius. The pressure potential is 4 bars. All right. Let's do this in red. So water potential equals your pressure potential plus your solute potential. Now, they just told you the pressure potential, right? Pressure potential is 4 bars. So that is 4 plus, now remember, solute potential is a minus ICRT. So it's minus I, which is your ionization constant. That's the number of particles it'll form. That ionization constant is 1 because it's glucose, right? So glucose forms 1 ring, so that'll be 1. Your concentration is 1 molar. You have that constant, so it's 0.0831. And then the temperature is 35 Celsius. So 35 plus 273. So we have to put that in Kelvin. All right, so again, I need to grab my phone here and do some math. Okay, so this number ends up being negative 25.6 plus 4, so minus 21.6 bars. So your water potential is minus 21.6 bars or bar. Okay. Well, hey, there you have it. The big thing to remember, water follows a solute, right? And it does that because when solute concentration goes up, water potential goes down. So keeping that stuff in mind, know that you have access to this chart with how to calculate solute potential and then the overall equation for water potential. So you got a practice document. I'd encourage you to work on that. And again, I'll have a little video that I'll post for that with a walkthrough of how to solve those problems. Thank you much.